Today we will continue our lectures on Ethernet because tutorial 3 uh, problems, okay, there are some problems from this topic. Let me complete this one, okay. Tutorial 3 will be discussed next week. Yep. So we have been looking at the basics of Ethernet, particularly towards the end we were looking at Ethernet MAC and also why there should be a minimum frame size imposed on Ethernet. So the minimum frame size should be 64 bytes, okay. So it should be imposed so that by the time jam signal comes back, the sender should still be transmitting the frame. So the frame transmission time should be at least RTT. RTT is upper bound by 51.2 microseconds. That's what we were looking at N. Okay. Now let's briefly look at the evolution of Ethernet. Okay. Ethernet uh, was it has been going through, okay, multiple stages, okay, since it was introduced in, for example, in late 70s or early 80s, okay. So initial configuration for this are in the form of what is called shared medium bus, okay. So whenever we say traditional Ethernet, okay, or maybe just Ethernet, we normally refer to the broadcast Ethernet or shared medium Ethernet, which is bus based. So this figure, okay, I've used this figure several times, okay. So you can see here that there is a linear cable. So this we call it as the Ethernet cable, which we also call it a shared bus because all the hosts are connected to this. They all use the same communication channel for communication. So at the end, okay, there are terminators. The signals are terminated here, okay. So it's called broadcast or shared medium because whatever uh, uh, is transmitted by, let's say, one node, for example, here node B, will be received by everyone else. So signals will be propagating on both sides. So since the frame will be received by everybody, okay, that's why it's called shared bus or broadcast medium. Okay? And we have seen that it will end up with the collision, okay. So when there is a collision, okay, it uses exponential backoff, okay, so that everybody can defer based on some probability, okay. So that's how it works. Okay? So here you can notice that every host has a chance of collision with every other host. Okay, that means if you put in a set form, okay, all possible hosts which can collide among each other, then this set will have all the nodes or hosts connected to this particular network. Okay, so in this case, A, B, C, D. Okay, so everybody can collide with everyone else. So this set we call it as collision domain. There is a single collision domain. That means there's a single set. There's only one set which contains all. Meaning is that everyone, okay, any member of the set, okay, has a possibility that has a possibility of collision with anyone else. Okay. And another key feature of this is that, okay, since it is the shared medium, okay, the total data rate or total throughput which can be achieved would be limited by, okay, the data rate of individual adapter or the network. Let's say this is a 10 Mbps network, and let's also assume that each adapter, okay, operates at 10 Mbps. That means whenever a host transmits, it can transmit at the speed of 10 million bits per second. Okay, so you take any 1 second, let's say during 1 second time period, A has transmitted NA number of bits, B has transmitted, let's say, NB number of bits, similarly C and D. Okay, this cannot be more than 10 million. Okay, though a host transmits at the rate of 10 million bits per second, okay, at any instant of time, at most only one can transmit. So if you put together all the bits which were transmitted or transferred or whatever it is, okay, you take any 1 second instant, okay, a small period, 1 second period, the total number of bits transmitted cannot exceed 10 million, okay, because it's a shared medium. Okay. Next, evolved what is called hub-based LAN. Okay, so this was popular from, let's say, late 1990s. Okay, so the configuration is slightly different. Instead of having a single cable, okay, along the walls or whatever it is, it has a small box hub, that's called box, a hub, okay, which has multiple ports, and the hub can be put in a room or lab or office somewhere according to the convenience of the configuration of the cables. And to that hub, all these hosts A, B, C, D will be connected. So this we call it as a star connected topology compared to the linear bus. Okay, and you can see here that the distance between any two hosts is more or less same. That is, the distance between any two hosts will be the distance between the sender host to the hub and the distance from the hub to the receiving host. Okay, and this hub is also a broadcasting medium. Okay. So it's not an intelligent device. What it does is, whatever bits it receives from a particular port will be copied into the remaining ports. For example, if B is transmitting a frame, let's say at the rate of 10 million bits per second, okay, these bits will be received at this port. These bits will be received at this particular port. And what hub does is, it mechanically copies the bits onto the remaining ports. Okay. When it receives from port B, it will pass it to all the remaining ports. When it receives from A, it will pass it to B, C, D. Okay. So eventually it's a broadcast. It doesn't look into the address of the frame or whatever it is. Okay. If it looks into the address of the frame, let's say B is sending to, for example, A, then it can forward to only A. But it requires some kind of intelligence. Okay, it should know where it is, etc. Okay, so it was simply a dumb device kind of things, some simple mechanical device. Okay, so cost-wise, it's cheaper. Okay, and what it does is, it receives this and send it to others. Okay, similarly, the jam signal also will be sent to others in the event of collision. Okay, because it's a broadcast one, there is a possibility of collision. Even in this case, the collision domain, there's only one collision domain, which consists of all the hosts connected to this A, B, C, and D. That means each of these four hosts has a chance to collide with everyone else in the same set. Okay? Is that okay? If we have set something like this, let's say A, B here, C, D here, meaning is that only these two can collide among themselves, these two can collide among themselves, but these two cannot collide among themselves. But it's not the case here. Everyone can collide with everyone else. So this has only a single collision set or collision domain. Okay. Again, the aggregate throughput here is only 10 Mbps because it's a broadcast medium. Okay. So that's what it says. All stations or hosts share the total capacity. A 10 Mbps hub line, for example, shared by all hosts. Total number of bits transmitted in 1 second can be maximum 10 million bits. Okay. But there are some differences between the bus and this. In the bus, okay, there is a long cable like this. Suppose the cable is cut for some reason, it cannot work as two different LAN. Okay, so the entire LAN operation will be affected because the signal need to be terminated at the end when they propagate both sides. Okay, but in the case of hub, there's no such cable inside. If at all there's any cable, the cable is from a host to the hub. So if this cable is cut, okay, or let's say A is not working properly or faulty or whatever it is, okay, the hub can still work with the remaining host. And the recent technology, which has been popular from, let's say, late 90s or 2000 onwards, okay, is switch. Of course, nowadays Ethernet switches are becoming cheaper and cheaper. Okay, they are more popularly used when compared to hub or the bus. Okay, so this we call it as switch based LAN. So if you can recall the definition of a switch. Do you remember the definition of a switch? Switch is not a broadcast medium. It's not a broadcasting device. Okay. A switch, this is how we draw normally. Okay. That means a switch receives some data from an input port and it forwards to some of the, let's say, one or more of the output ports. That means the process of forwarding data or frame or whatever it is received from a port to an appropriate output port is called switching. Okay, it's not broadcasting. Okay, so Ethernet switch is also based on switching. Okay? See, for example, maybe look at this figure. So this is a switch to which all the four are connected. So note that in the example we have used the same four hosts. In the first one we used the bus to connect. In the second one we use hub to connect. Now we use a switch to connect all the four. Okay? So what makes the difference here? Okay. So now you can see that there can be more than one simultaneous transmission happening here. It's not a broadcasting device. See here, B is transmitting to A and C is transmitting to D. So here B is transmitting to A, here C is transmitting to D. So both transmissions can take place simultaneously. How? Because this is the switch. Okay. This is something like store and forward switch or accept and forward switch, and there are buffers inside this. So if you can recall this STTM or statistical TDM or the switches or routers, okay, they all use buffers. Okay, so this is an intelligent device in the sense that when B transmits a frame, okay, it receives it and it looks into the destination address. If the frame destination address is A, then it forwards to only this particular port. It will not broadcast to all. Similarly, when it receives a frame from C, it looks into the header, okay, then, okay, let's say it's meant for D, then it will forward it to the port to which D is connected or to the port through which D can be reached. Is that fine? If there is some transmission going on here, then this frame will be put in the buffer, in the queue. So very simple. A frame is received, look into the destination address. Here the destination address is the Ethernet MAC address or hardware address. Okay, then it will forward to only that particular port. Okay, and it may be queued there depending on the demand. Okay, if there is no transmission ongoing, this will be transmitted immediately. Otherwise, that will be waiting in the queue. Okay, there is no collision and other things. Is that fine? So the maximum number of transmissions here, what is that? Every host can transmit at the same time. Okay, so B can transmit to A, C transmits to D, A can also transmit to another one. Similarly, D can also transmit to C or A, doesn't matter. Okay, so every host can transmit. Is that fine? As long as the buffer can hold inside, there's no issue at all. Okay, so the maximum throughput which can be achieved would be n times 10 million, n times 10 Mbps. Okay, assuming that each host operates at 10 Mbps, that means each host can transmit maximum of 10 million bits in 1 second. Okay, so the total throughput or maximum throughput or capacity here could be maximum n times. N is the number of hosts connected. Here 4 times 10 Mbps. So it's a great advantage of this. Similarly, the collision domains. There is no collision between AB, AC or AD because they are all connected to different ports. Okay, so the collision, there will be 4 collision domains here. The first collision domain is A, the second collision domain is B, C, D. That means if there is any collision for A, and that will be the collision onto itself at this port. Okay, what does it mean here? Here, in this case, to this port only one host is connected. But it may so happen that to this port, okay, a hub can be connected or a broadcast network can be connected. Okay, so if there are hosts like A1, A2, A3, A4, let's say this is the hub, okay, which is connected to this particular switch, okay, then the collision domain will be those hosts connected to this port, that is all these four. That's what is given here. If at all there is any collision, that the collision is only within the same port, not between the two ports. A good example of this is fast Ethernet. Okay. The standard is 802.3U. It's 100 Mbps Ethernet switch. Okay. The notation here is 100 base T. So if you recall, 100 stands for 100 Mbps. T stands for twisted pair copper wire. Is that fine? Okay. And it can also support optical ports, optical transmission. Okay. So which we call this as gigabit Ethernet. The standard is 802.3Z. We are not going into the specifications of all these standards. See, for example, the notation here, the different standards are here. 1000 base SX, 1000 base LX. 1000 stands for 1000 Mbps. That means 1 Gbps. Okay, 1 Gbps. And SX, what is this SX and LX? Okay, that's with respect to the optics, optical transmission. SX means, okay, the transmission is, okay, on 0.85 micron, which we call it as short wavelength. S stands for short wavelength. Okay, multimode fibers, the mode of fibers, the kind of fibers used is multimode fiber. We don't have much time left to discuss about this, but I believe you must have studied multimode, single mode fibers in physics in the school or year one or sometime. Okay. LX stands for long wavelength. It operates at 1.3 micron wavelength. Okay. Any doubt? What is important to note here is that this Ethernet is basically a plug and play device. Okay. So without any change in hardware or software of the attached stations or computers or hosts, a bus line can be converted to hub or to a switch. That means today you can connect these four to a hub. If you replace the hub by a switch, still it will work. You don't need to set any additional configuration or update the firmware, change something onto the host and other things. Okay, so this will simply work. It's not like router, which we will see later in the tutorial, which may require some additional configurations and other things. But here, these devices are just plug and play devices. So this figure shows maybe a simplified Ethernet-based switch in a campus or enterprise network. Okay. So usually, as I said before, nowadays we don't have one single network, but it could be a small local area networks connected by multiple switches at different level. Okay. Maybe at the lowest level, inside, let's say, small office or room or a small lab or something, we can have hub, 10 Mbps hub. But as I said before, okay, hub are not that popular now because switch, the cost of switch is also very small. Okay, it's not that expensive. So maybe instead of hub, we can very well use directly switch. So it's a 10 Mbps hub. Maybe in the next level, okay, so we can have maybe 10 or 100 Mbps switch. Okay, so the port data rate could be 100 Mbps or 10 Mbps. Okay, maybe just you can imagine that there can be small network in one lab or one office, one this floor, that floor. So they all can be connected by different kind of switches at different levels. Okay, but at the highest level, okay, when all this data goes up, okay, they are all finally connected to some servers. Okay, usually these servers nowadays are kept in data centers. Okay, see for example, our university has some data centers where uh, multiple servers are there. Okay, all the services, storage, everything, they all come from there. Similarly, every enterprise, okay, company can have servers in the data centers. So, but those servers have to serve so many devices, users. Okay, so the capacity of this link at that level would be a high capacity link. Let's say it might use gigabit Ethernet, 1 Gbps. But when it goes further down to small labs or offices, it can use 100 Mbps ports or 1 Gbps ports or 100 Mbps switches. Again, it's just an example, okay? But the campus may have more complex connectivity, but what's important to show here is that there exist many small local area networks could be connected by switches at different level. Okay? So I put a cloud here. The meaning is that this kind of configuration can repeat here. This could be from one particular building to that server. Maybe similarly there may be for other buildings, other departments, offices, they may have similar connectivity. Any doubt so far? So let's move on to the next topic, okay, which is an important and interesting topic, because as I said earlier, nowadays switches are used when compared to maybe the bus or hub. Okay. Now the question is, when we use switches, okay, how we can interconnect multiple LANs, local area networks. Okay, as we have seen before, as per the Ethernet standard, a local area network, okay, has some limitations. That means one network can be up to 2.5 kilometer long. I mean, in terms of cable, maybe one whole buildings or few floors, this you can connect or something, okay. But if you connect more and more devices to broadcast kind of network, okay, there's a higher chance of collisions. Am I right? So the trend here is that we can have small local area networks and connect them through switches. Connect them through switches, because if you look at from the collision perspective, okay, between the ports there's no collision. It's only forwarding. Okay. If as long as the buffer is there, it can go and wait in the buffer associated with that particular port. If buffer overflows, okay, there will be congestion or dropping of packets, etc., or frames. Okay. So what we are going to look at here is bridges and extender lines. When we say bridge, so you can imagine that a bridge is similar to switch. Okay. There are small differences. Okay. Historically, still, when you read the book and all, still they use bridge. When you look at the protocol, they define with respect to a bridge. But in the current context, you can imagine that a bridge is a switch, like a box with multiple ports. Okay. Because earlier, maybe in 1990s or so, okay, when it was felt there's a need to connect multiple local area networks, okay, maybe in 2 different buildings or 2 different labs or something, okay, they used to have what is called a bridge, a device which connect, let's say, this Ethernet LAN and this Ethernet LAN. This bridge usually have maybe few ports, 2 ports or 4 ports kind of things. There are some restrictions, okay, but switch, it can have many number of ports. Okay, there are small differences. Let's not worry about this. So whatever we discuss here in the name of bridge, okay, applies to switch. Okay, so when I say bridge, you can imagine, let's say, Ethernet switch. When we discuss, let's say, spanning tree protocol for the bridge, so you can immediately relate, okay, this a similar protocol. This protocol is running on Ethernet switch or Ethernet switched network. Okay, so we call this as ELAN or extended LAN, because multiple LANs can be connected by one or more switches. Now look at this. So there is a local area network N. So LAN here, there is a LAN 1 which has ABC. are connected to this LAN. There is another LAN 2 where A, B, C, X, Y, Z are connected. These are the two LANs, okay. But these two LANs are connected by a switch or bridge, okay. Is that okay? So the advantage is here is that if there is any collision, the collision will be between A, B, C, okay, and the transmit. If there is any collision, it will be within X, Y, Z. Transmission from A to X, Y to B, that will be forwarded by the bridge or the switch. Is that fine? Okay, so this is a typical connectivity, or is a very simple example. You have two LANs connected by a bridge with just two ports. Okay. Now the question is this. Okay. When a frame is sent by a host, let's say A wants to, let's say A is the source address. A wants to send a frame to X. So it prepares the frame. If you look at the frame format, there's a destination address where X is written, where source address, where A, the MAC address of A is written. So the frame carries the two addresses. Okay. So this will be, okay, A will broadcast it on this LAN, LAN 1. Okay. So we need to do something more to deliver this particular frame to X, because it is connected through a bridge or switch. Is that fine? And this bridge or switch operates in promiscuous mode. Okay. So what does it mean? A switch can accept all the frames. It's not like our host. Our host can accept only our own frames. Other frames cannot be accepted. Okay. But switch can see and can accept all the frames. So when A is received by this switch or bridge, okay, A look into the address, destination address. Okay, destination address is A, X. Then it can make a decision what it should be done with this. Okay, if the switch knows that X is on this particular LAN, then the switch can forward the frame through this particular port. Okay, then it would be easy for X to grab it. Am I right? So basically there are two approaches in forwarding frames between local area networks which are connected by a bridge. Okay, in the first approach, what is done is, okay, is that the complete address or path information is given. That we call it as source routing bridge. That means when A sends some frame to X, it should indicate that, okay, it should go through, let's say, switch 1, bridge 1 to reach X. Okay, the complete information should be given. Or if you look at a more complex example, let's say something like this. There are many switches or bridges connected. All these blue color lines are the local area networks, A, B, C, D, etc. So it has to see, for example, let's say A wants to send it to J, then A has to tell, okay, this frame will be forwarded through, see, for example, B5, B1, B5, B1, B4 before reaching J. So that complete information should be given at the source. Then it is called source routing bridge. Okay. This was promoted by the Token Ring Group 802.5. Okay. But this is not popular now because it's more burden on the source. It should know that there are many switches or bridges before reaching the destination, and it also should tell how to reach that. Okay. So instead, we want to have a simpler mechanism, okay, that, okay, whether A sends to C or A sends to X, whether it goes through one switch or no switch, or whether the frame should go through multiple switches, okay, it should be completely transparent. In the sense that A will send a frame to X as if that is in the same local area network. Okay. For example, if A sends some frame to C, when it's broadcast on this LAN, C will grab it. Am I right? The same way only A wants to do that. A will just specify, this is my destination address. Okay, whether it is C or X doesn't matter. and A does not want to specify or know that X is connected through a switch. Okay, is that okay? Then this kind of switches which support this are called transparent bridges. Okay, that means the host need not do not have the knowledge of the presence of the bridges or switches. So as if they are all in the same local area network, they simply send the frame. This is popularly used now. This is also called spanning tree bridge, which the meaning which we will understand okay very soon why it is called spanning tree bridge. Okay, is it clear? Any doubt what we mean by extended LAN? Okay, this is something like multiple LANs connected by one or more switches. Okay, hereafter we are considering only the transparent bridge or spanning tree bridge. Now for the transparent bridge, okay, the burden is not on the host because host doesn't need to do anything. It just simply send its frame. Okay, but the switches need to do something more to forward the frame from A to X. The switch should know that okay, the host X is located on this side. Okay, okay. Similarly, the switch should know that A, B, C are located on this side. Okay, and X, Y, Z are located on this side. Why? Because whenever it receives a frame, if the destination address is say Y, then it will forward it through this side. It will send the frame through this port. Okay, when it receives a frame whose destination address is let's say C, then it will forward it to this left side, this port. But this information should be known to the bridge or switch. So how it learns, how the switch knows that X, Y, Z are here and A, B, C are here on this port. Okay, and this learning is not static, it is dynamic. What do you mean by that? Because X may be connected to this now, maybe after 1 hour, okay, we can remove this host and we can connect it to this port. It's possible. Am I right? So this can be dynamically changing. So it should continuously run some protocol, some method by which it can learn, okay, A, B, C are this side. Now X, Y are this side. Oh, now X, Z is on this side. So it should know, it should learn. How it learns? It's a very simple method, okay. So what's the purpose of learning? Once it learns, it knows, okay, where the particular hosts are located. It maintains what is called a forwarding table. Each switch has a forwarding table with 2 entries, let's say 2 fields. So 2 fields, host and the port. So what does it tell? For every host in the whole network or extended LAN, okay, this as you can see this as a whole bigger network, okay. For each host, the bridge will record the port through which it can reach. For example, here A, B, C are connected to port 1. Port 1. X, Y, Z are connected to port 2. This information is available in the local forwarding table. Is that fine? But how it builds the forwarding table, we will see it. Okay. Assume that it has built the forwarding table, then forwarding would be easier. Okay. Suppose it gets a frame whose address is Z, then it will forward it to port 2. Okay. So now the question is how it builds this table. How the switch knows that A, B, C are on this side, X, Y, Z are on this side. Okay. So that it uses a very simple method which we call it as backward learning. It learns based on the source address. Okay. We look at the method now. Okay. Before that, I mean, if the frame carries broadcast address, obviously it will forward it to all the remaining, all the ports. That means all the remaining ports. What's the broadcast address? All F, 1111, F, 6F, okay? Is that fine? Yeah. Now, initially the forwarding table is empty. Forwarding table is empty. So if a frame is received, if the switch does not know where the destination address is, whether it is on port 2 or port 3, 1, 4. It may not know. If it does not know, okay, where the destination is, then the switch will send it to all the ports. I mean, all the ports except the port from which it has received. Okay. Let me explain through an example of this backward learning. It's called backward learning because whenever it receives a frame, okay, it tries to learn, okay, uh, from where this particular frame is coming through. Okay, very simple. Let's say a switch is here with two ports. Okay, port 1 is this side, port 2 is this side. When it receives a frame from here, let's say the source address is A. The source address is A. Okay, okay. Then it learns that host A is on this side because it's receiving a frame whose source address is A. But can it learn where the destination is? It does not know. Look at this case. Let's say initially the forwarding table is empty. Now the bridge, there's a switch, receives frame AB, A comma B. Assume that A is the source address, B is the destination address. Okay. So this frame will be received here at port 1. Okay. So since the forwarding table is empty, it does not know where B is because destination is B. It does not know that B is on this side. Okay. So what it will do, it has to broadcast that frame. Broadcast here means it has received the frame from port 1. It will send it to all the remaining ports. Here the remaining port is only 2. If there are other ports like 3 and 4, it will be sent through 2, 3 and 4, not to 1 because it has received from 1. It doesn't need to send it back to the same port. But at the same time, it learns that A is on port 1 because it receives a frame with source address A from this side. Okay. Is it okay? So an entry for A is made in the forwarding table. This is the forwarding table. Okay. Now let's say there is a frame YA is received. YA means Y is the source address, A is the destination address. Source address and destination address. So this will be received from here, port 2. So it receives a frame from here. It looks into the source. Source is Y. Okay. That means the host is on this side. Y is on this side. So immediately it will record Y2. Now A. The destination address is A. It has an entry for A. That means it will forward it to port 1. Is that fine? Now let's say BZ is received. BZ will be received on port 1. So it knows that B is on the side of 1. That is, B can be reached through port 1. What is the destination? Destination is Z. There is no entry for Z here. So it will broadcast that frame. That means it will send the frame to all the remaining ports. Now it receives C comma B. So C comma B will be received through this port because C is on this side. So it learns by looking at the source. Now it makes an entry for C. C can be reached port number 1. And the destination is B. It has already learned B. B is on port 1. Okay. Note that it receives a frame from C that is on port 1. And the destination is B, which it knows that it is on port 1. So what it should do? Will it forward or will not forward? It will not forward because it knows that B and C both are on the same side. Okay. Any doubt? Okay. So this is a very simple example. You have just one switch. Okay. There are only two LANs, but an organization may have a complex network, something like this. Okay, because there are many offices. Okay, in the same floor, different floors, labs, etc., okay. And for administration or maybe other reasons, there will be connectivity, something like this, okay. So when there's a connectivity here, you can see that there is a loop, something like this. Loop means a cycle, okay. Maybe let's consider a simple case. Look at this case, B1, B2 connected to A and B. So this A and B are LAN. This is a LAN, this is another LAN. So this is B1, B2. Why we should have two switches here? One good reason can be reliability. Reliability means, let's say if B1 becomes faulty, still A and B will be connected through B2, another switch, okay. There's a fault tolerance or reliability is there, okay. Or maybe for the reasons of administrations, okay, this is one line is on this, they have a switch, another line is on the other floor, this another switch, okay, can have multiple switches, end up with a loop, okay. If there's a loop, okay, then when we use the so-called learning bridges or something, okay, that would be some problem, serious problem. What is the serious problem? Let me explain with an example, okay. Let's say there's a frame F which is received on this. B1 receives some frame F, okay. It receives frame F, and let's say the destination is not known. That means there's no entry in the forwarding table. It's a new destination. It sees it first time. So what it will do? It has to send it through all the remaining ports. Here there's only one remaining port, so F1. Let's say it forwards the frame to this port on, let's say, LAN A. Because it has received from this, so it forwards to this one. Let's call it as F1, frame 1, just for our reference, okay. So this frame 1 is received by B2. Let's say B2 also does not know the destination. Then it will forward to this port, F2. So it receives F1 here. So it forwards to F2. We call it as F2. When F2 is received here, it still does not know the destination. So it will forward through the other LAN. It generates a new frame, transmits it again. Okay, that means we call it as F3. F3 is received here. Still B2 does not know the destination. So it transmits onto the other LAN. We call it as F4. So it will continue forever. It will continue forever because it does not know where it is. So it will put here, then put here, put here. So this problem arises because there's a loop. There's a cycle here. There's a loop here. So it will be looping around this. So this is a serious problem. So we do not want to have such loops or cycles in the topology. Topology is the pattern of connectivity of the extended LAN. Okay. So how we are going to avoid or break this particular loop is what we are going to look at now. Okay. So as I said before, the trees are also called spanning tree bridges. Okay. So what we are going to do is this. We are going to create a tree of bridges or LANs. Okay. So through which the forwarding will take place. That means we may have very complex topology, something like this. This has multiple loops. See, there is a loop here, there is a loop here, there is, okay, there are two loops here, okay. So we don't want this loop to occur. Okay? We are going to use spanning tree for forwarding. Okay. What is the spanning tree? How many of you are familiar with spanning tree? Can you raise your hand? You might have studied in basic data structure or algorithm, this, that. Am I right? Okay. So you know that a network can be represented as a graph, something like this. Let's say this is the switch or router, and the edges are the links. So this is called a graph. This is called a graph. Okay, but here you note that there exist multiple paths or loops. So you can see this is one loop, this is another cycle, another cycle. Of course, there is a bigger cycle also here. Okay, so there are multiple loops here. Okay, because of the loops, there exist multiple paths. For example, you take one, you can reach, let's say, this particular node either by this or by this. Okay, is that okay? So if there are two paths, I mean, we need to have more intelligent routing method, whether to send it through this or something. Okay, but if we restrict to only one path, okay, between two nodes, if there exists only one path, okay, then it's easy to forward because the forwarding will take place only through that particular path. Okay, so we define what is called a tree. Okay, it's a spanning tree of the graph. Okay, because it spans all the nodes. Okay, that means we create a tree from the graph, but all the edges will not be there. We are going to remove some edges to make it a tree. Then what is a tree? The tree has some features or characteristics. There are no loops. In tree, there should not be any loop. And there is a root in the tree. One of the nodes, you can treat this as root. And there is a unique path from the root to any other node. Similarly, if you take any two nodes, there will be only one path. This is something like the tree on the road. The tree has a root. Am I right? It has some branches. It has some branches. Okay? So how do you reach from one branch to another branch? How many paths are there? You take any one branch, you take another branch in a tree. In how many different ways you can reach that particular branch? Let's say branch A to branch B. Is my question clear? Yes? There's only one way. Unless you jump from one branch to another branch, let's say you are not allowed to jump from here and there. Okay, you see that there's only one path. There's only one way you can reach from a given branch to any other branch. Okay. Similarly, tree is also defined in the same way. So if, see for example here, this is the graph. There are two trees shown here. Two possibilities. Of course, there could be more than two possible trees. Here, node 1, we call it as the root. Okay. In some cases, it has some specific purpose. Okay. Let's say this is the root. Okay. And you can see that here there are loops, but here there are no loops. Okay. Similarly, it's a connected one, connected graph, and you take a node. Okay. There exists a path to every other node, but there exists only one path between any two nodes. You take 1 and 5, 1 and 4, there exists only one path. Okay. You take this, for example, here. In this case, you can reach in two ways, but here you can reach in only one way. Okay. Is that fine? So these two are the trees. And one of the trees is called spanning tree or shortest path spanning tree. Okay. So what do you mean by shortest path spanning tree? Very simple. Okay. You take this original graph. Okay. If you consider the shortest paths from the root to every other node, and if you combine all of them, we call it as shortest path spanning tree. Maybe I put in a simpler term. Okay. If you take any two nodes, or let's say a node 1 and the other one. See, for example, here, let's say this is node 2. You take 1 and 2. There are many paths here. You can go this way, okay, this way. There are many paths from 1 to 2. But the shortest path is this. This is the shortest path. Am I right? 1 to this node and this node. This is the shortest path. The same shortest path is there here with the same two hops. Is that okay? But if you look at this tree, this shortest path is missing. For this tree to reach, let's say node number 2 from 1, you have to take a long path. For example, 1, then here 1 hop, 2 hop, 3 hop, 4 hop. So you need to traverse 4 edges to reach this. Okay. So the shortest path in the original graph is preserved here. It's not here. Similarly, you take any 2 nodes here, here. You can see if the shortest path traverses 2 edges, here also traverses 2 edges. Okay. So we call this as shortest path spanning tree. Shortest path spanning tree. Okay. And so what we are going to do is we are going to remove the loops from the extended LAN. We are going to create the shortest path spanning tree by using the a protocol which we call it as distributed spanning tree protocol. Can I continue for another 10 minutes? You have any lesson after this? Yes? Okay. So sorry taking more time, but we are anyway next week we have to do one more lecture notes and a tutorial. Okay. So now we are going to look at the spanning tree algorithm. We are not going into a detailed theoretical algorithm. Okay. Some of you might have, or at least the computer engineering students might have studied in your other courses. Okay. The spanning tree methods or spanning tree algorithm. What we are interested here is that the protocol, how it works. We call it as distributed protocol because all the nodes in the graph will participate in the process. They all exchange few messages here and there, and they finally decide, okay, this is the tree. Okay. So in this particular case, okay, but slightly different from the conventional network here. When you create a tree, okay, it will have all local area networks. For example, local area network A, B, C, D, K. Okay, there are many local area networks drawn as blue lines. We need to retain all local area networks, but we are going to break the loops. There should not be any loop. Okay. See, for example, you look at the dashed line. So if you remove this and this, this loop is broken. So this is the loop here. Similarly, there's another loop here. So if you break this link and this link, okay, and there's no loop here. Am I right? So basically, we need to decide which of the ports should be active, which of the ports should not be active in forwarding the frame. Physically, they are connected. Bridge 3 is connected, bridge 6 or switch 6 is connected. But we are going to declare at the end of this algorithm or protocol that, okay, this particular port should not be active. That means it should not forward any frame. Similarly, this should not forward any frame. So this is the restriction we are going to impose. But now the next question is, how are we going to decide which port should be active, which port should not be active? Okay, we need to make sure that every LAN should be able to communicate to every other LAN. Okay. Okay, so the first step is we are going to choose one of the bridges which are all alive or powered on or active as the root. As the root. Okay. So we choose the bridge with the smallest ID as the root. So everybody will be sending some messages, and at the end of this protocol they agree that, okay, for this case B1 is the root. Okay, but it's not predetermined. It's not pre-configured. Say, for example, if B1 becomes faulty or B1 is powered off or anything, okay, then B2 should take over as the root. So among the bridges, the one which has the smallest ID will be elected. It's a kind of election as the root. Okay. Then we will create the set of shortest paths from every bridge to the root. Okay. So if we find the shortest path to the bridge, to the root from every other bridge, okay, then it will form a tree, shortest path spanning tree. Okay. So now the question is how we are going to find the shortest path to each from each bridge to the root. Okay. Okay. Now you can see that there is a, for every LAN, one of the bridges or switches will be called as designated bridge. For example, look at this. This is LAN A, which is connected to, physically connected to B3 and is also connected to B5. Okay. So if it has multiple connectivity, if it can forward through 2, then it will end up with multiple paths or loops. Okay. So in terms of for the purpose of forwarding, one of these will be selected as the designated bridge. So in this case, for example, for LAN A, B5 may be designated bridge. How it's decided? Because B1 is this example. B1 is the root. So you take A, how to reach, let's say for example B3, how B3 can reach B1. B3 can reach this way, B5, then B1, B3, B5, B1. Okay. The other one is B3, B2, B1. Okay. But for LAN A is concerned, if it goes through, if it sends frames through B5, B2, it has to send through B5 then B1. But if LAN A has to send frames, it has to send through B3, B2 and B1. It's a longer one. Am I right? So this may be a better choice of the designated bridge. Is that okay? And when the algorithm runs, okay, or even after data frame, the frames will be forwarded through only the spanning tree. Okay, now we are ready for the algorithm or protocol. I am going to explain this protocol with an example. Okay, we again take this part as the example. Okay, this is the loop. We are going to see that how we are going to break the loop. How we are going to decide that this port and this port will not be active, so that the loop is broken. Okay. Each bridge exchange some messages. We call it as configuration message, which is basically a triplet, which has 3 fields: Y, D, X. Okay. What's the meaning of this? X is the identifier of the sending bridge. Okay. X is the sender, and X believes that Y is the root. It believes, because they have to arrive at a consensus. Okay. Who is going to be the root? Who is going to be the leader? Okay. And the distance from X to Y is D. Okay. So initially, when the algorithm or protocol starts, everybody will think that, okay, everyone thinks that he is the leader. He is the one with the smallest ID. That means everyone will send something like X, 0, X. That is, X is the sender. X believes X is the root. He is the root. The distance from X to X is 0. Okay. That means B1 will send B1 0, B1. B2 will send like, okay, because nobody knows who has the smallest identifier. So everybody declares that he has the smallest identifier, that messages will be spread out. But if a bridge gets a configuration message from another bridge and it finds that that particular bridge has a smaller ID than this, it gives up. Gives up means it accepts that, okay, this fellow is the root, I am not the root. Okay. But this has to be sent through other people, because earlier it broadcast that, okay, he was the root, but now it changed the decision that there is someone else, okay, who has smaller identifier than him. Then he will send a new configuration message. Okay. But after some time, when the designated bridge is fixed for everybody, it will stop forwarding the configuration message. Okay. Again, I'm explaining with the help of an example. I'm not showing all possible configuration messages, because maybe initially it will be flooded. Everybody sends configuration message, goes here, but they will slowly converge. After some time, everybody will agree that, okay, B1 is the root. He is the one who has the smallest identifier. Okay. I'm showing a subset of the messages, okay, which are essential to make you understand the concept of breaking the loop. Okay. I'm not showing all. Again, I'm showing this example. Oops. Only for this loop. This loop means involving B3, B2, B5, B1. Okay. So let's start arbitrarily from some point. Let's say B3 receives a message. So B3 receives a message on LAN C. This is LAN C. So B3 receives a message B2, 0, B2. That means B2 has declared itself as the bit. This is the sender, this is the root, the distance is 0. Okay. When B3 receives this, what B3 will do? It will accept B2 as the root because its own ID is 3, the other fellow ID is 2. So it accepts B2 as the root temporarily. Okay. At this time, this is the best configuration message he has received. It sends this message on the other LAN. That is, this is LAN A. That means it says that, oh, I received some configuration message. I understand B2 is smaller than my own ID. So I accept B2 as the root. And it says, okay, the distance from B3 to B2 is 1. This helps to calculate the shortest path. So B3 is the sender. B3 accepts B2 as the root. The distance from B3 to B2 is 1. In one hop, we can reach from B3 to B2. This is sent here. Okay, there are similar messages going on here and there. But let's say B2 receives a message now from B1. Okay, B1, what it sends? It sends B1, 0, B1. So this part. Okay, so it receives B1, 0, B1. So B2 has to accept that B1 is the root because 1 is smaller than 2. So what B2 will do is it prepares a new configuration message. Sender is B2. It believes B1 is the root and 1 is the distance from B2 to B1. And this message will be sent on LAN C. Okay, earlier it sent this message, but now it changed its decision. It sends a new message, this. This one. Okay, similarly, this B1, 0, B1 will be sent to here also. So B5 receives a similar message, B1, 0, B1 on LAN D. So B5 accepts B1 as the root because 1 is smaller than 5. And it sends another message, B1, 1, B5 here. That means B5 is the sender. It believes B1 is the root. 1 is the distance from B5 to B1. Now, this message was sent to B3 from here. And there's another message sent from B1 here. Let's say B3 receives this message, B1, 1, B2. Okay, so now what B3 will do? Now B3 accepts B1 as the root. B3 accepts B1 as the root because earlier it was thinking B2 as the root. Okay, now there is another one. B2 declares that B1 as the root, so it has to accept B1 as the root. Okay, and at the same time it does something more. What it does? Okay, because it receives this message on this LAN C. Okay, from B2, it understands that LAN C is connected to B2 as well as B3. Okay, and B2 is closer to the root. B2 is the closer to the root, so it stops forwarding to LAN C. So this link will be cut. This link will be cut. Cut means physically it is connected, but it will not forward any frame through that port. Okay. Similarly, when it receives the message B1, 1, B5 from here, okay, it accepts B1 as the root, but at the same time, it understands that, okay, B5 is closer to the root, okay, when compared to B3, and this receives on this LAN. So LAN A is connected to B3 and B5, but B5 is closer to the root. B5 is closer to the root. So what it will do? It will declare that this port is inactive. So it will stop forwarding to LAN A here. That means eventually physically B3 is connected, but these two ports will be inactive. So you can see that there is no loop here. Similarly, this loop and this loop will be broken. When the loops are broken, it will have a spanning tree. So what the root will do is it will periodically send the configuration message. Periodically it will declare that I am the root, I am the root. That message will go through the tree. Why it has to periodically declare? Because everybody should know that root is active, because it's a tree. Even if you cut one particular link on the tree, okay, some will be disconnected. Is that okay? So if B1 is faulty or powered on or whatever it is, powered off or whatever it is, okay, then the configuration message, periodic message will not be received by others. Then everybody will start the algorithm again. Maybe they may start declaring that, okay, I am the root. Okay, then the same thing will continue. So if B1 is faulty, maybe B2 may take over. So in this case, maybe different ports, different set of ports may be inactive or active. Okay. Again, I show only a subset of configuration messages which are used to help break the loop. Okay. Is that okay? There is a theoretical proof how it converges. It will eventually converge. Everybody will agree on this, that we are not interested in the theory, but we are interested in the protocol, how it works. Okay. Let me stop here. Sorry, I took long time. Okay. So we will see on Monday. Monday we look at the wireless LAN, the Wi-Fi 1. Then Wednesday we will discuss tutorial 3.